Hi guys, a very good evening. Right, there's a lot of movement in my house, so I don't want to open my camera. Right, if it is required, we'll see. Okay, fine. So just give me a minute. I think I will be made host in that time. Just I need to now download the PPTs. Okay, let me share my screen. Okay, I hope everybody is able to see my screen. Right. Right. The first question. Let's see. I mean, chapter it is. I think this is the last chapter, right? Any other chapters left? Nice. Guys, are you able to hear me? Hello, guys.
Yes, sir.
Okay, I think it's a little lagging. Fine. Right. First question. Right. Which of the following is the correct order of okay. Which of the following is the correct order of ease of coupling with C6H5N2 plus and Cl minus? We know what coupling reaction is, right? So coupling reaction, you have to understand that this is how coupling reaction happens, right? Say we have your diazonium salt N2 plus Cl minus, and say we have some Z group here, and that para hydrogen will be taken like this, and we will be forming N double bond, two benzene ring like this will be attached, right? This is what is called as a coupling reaction, and these are what are called as azo dyes. They'll be colored. Okay, there'll be orange. This, for example, this example is going to be yellow colored, right? Okay. Now, depending on what is this Z, this reaction is going to become more and more easy, right? Now, please understand that Z should be a electron donating group, right? Electron donating group will increase the rate of the reaction. Electron withdrawing group will decrease the rate of the reaction. Okay. Now, benzene has nothing, just benzene, right? So definitely it is not going to be the highest, or it's not going to be the least also. We'll see what is going to be there. NO2 group is electron withdrawing group. Phenol is electron donating group. This is okay, right? Now, this is electron donating as well as electron withdrawing. So we'll keep it as electron donating only, right? Fine. So out of these, only one strong electron donating group here is phenol, that is OH, and okay, electron donating group, which is chlorine, right? So first should be three. Right? Fine. Okay. Now I think chlorobenzene, when I make it react, when I compare it with benzene, we say that chlorine is ortho para directing, but it is deactivating, we say. What do you mean by deactivating? It is going to deactivate the benzene ring towards your electrophilic aromatic substitution reactions. Right? So when I compare benzene and chlorobenzene, when I say it's deactivating, means benzene is going to be more reactive. And nitro is also deactivating, but it's okay. But here it will be deactivating by inductive effect. Here it will be deactivating by minus R effect in case of nitro group. Here it will be minus I effect. Here it will be plus R effective, right? This one, phenol, right? Anyways, so the answer should be 3. After that, 1 should be there. So that is D should be the answer to this question, right? Okay, moving on. Okay. In a set of reactions, meta-bromobenzoic acid gave product D. Identify product D. Okay. So this is what is meta-bromobenzoic acid. First, if I go for SOCl2, what will you get? That is a chlorinating agent which will convert your acid to acid chloride. COCl it will become. And this Br will be like this only. Right? And then you're going for NH3. Now that will convert your acid chloride into your amide. That is C double bond O. NH2 will come. That is simple. H from this thing, Cl from this thing. And Br is also there. Right? And your NaOH for Br2. What reaction is this? What is this reaction, guys? NaOH for Br2?
Half-man's bromine.
Yes, half-man bromide reaction. So what is going to happen in the reaction? So if I have an RC double bond to NH2, and that if I go for Br2 and KOH or Br2 and NaOH, one carbon atom will be decreasing and you're going to form RNH2. This carbon atom, C double bond will be gone. Same thing, this C double bond will be gone if I go for NaOH and Br2. And you have to attach this benzene ring with nitrogen. As simple as that. So we will get, okay, I'll write it here. We will get NH2 here and Br is still going to be remaining. That is what is the answer. NH2 and Br in meta positions. That is option A. Okay. Right. Next. Sorry. In the following, are you able to see everything, guys? This is small for you.
So, yes, sir.
It's
This question is very small.
Okay. Right. So is this fine?
Yes, sir.
Okay. Right. In the following reaction, this and this reacting with NaOH, right? Fine. Now what is going to happen? Okay. Now you see that basically HCl is getting removed. Basically, an aniline reacts with your acid chloride to form a secondary amide. This is an example for a secondary amide. Right. What reaction is this? Right. Now you understand it's Perkin reaction. You're not doing anything. Scott-Bowman reaction. What is Scott-Bowman reaction, guys? Do you know? If you have N2 plus Cl minus, if you may go for BF3 and heating it, what will you form? Guys, if you have N2 plus Cl minus and BF3 and heating, what will you get?
Fluorobenzene.
Fluorobenzene. And this reaction is what is called as your Scott-Bowman reaction. Okay. Friedel-Crafts reaction, we know. Friedel-Crafts reaction in the benzene ring, something should happen. Electrophile should come.
Sir,
That is not, yeah.
Sir, then what is Walskimann's reaction?
Perkins reaction. Perkins reaction is not worry, Kana. That is way
Sir,
beyond.
Walskimann is.
Oh, I think this is Balskimin only. Sorry, this is Balskimin. Right? Scott-Bowman is this. Let me make a page, or let me ask. Okay, if I can write. Scott-Bowman, I think, is if you have. Oh, I think the first reaction. Okay. Oh, this is, I think, Scott-Bowman. D. Yes, I will just confirm it. Just a second. I think whatever the reaction is given is called a Scott-Bowman reaction. RC1H2 eventually forming this thing. Yeah. The reaction is Scott-Bowman. Reaction answer is that one. Right. Okay. So the answer of this question would be B. Right. Whatever this reaction, whenever your aromatic, this particular ring is coming and attaching with nitrogen, that kind of reaction is what are called as Scott-Bowman reactions. Okay. All right. Moving on. Oops. Right. The preferred set of reagents required for the following conversion is, right? Now, what I'm understanding is that I have an iodine getting converted into NH2. I will see what can be done. And same number of carbon atoms, right? If I just, right. You just see the same number of carbon atoms also there. Is it not? Okay. That is between this and this, we have same number of carbon atoms. That means if you go for, okay, now if I go for alcoholic casein, what happens? Alcoholic casein is actually like alcoholic KOH. Basically, I'm going to form an alkene, right? And to that alkene, you're adding concentrated HCl, nothing will happen. Okay, you will not get this one. Okay. Next, if you make it react with NH3 at 373 Kelvin in copper tube, that makes sense, right? For example, if you have CH3, if you have Ri, right? And if I make it react with ammonia, you can form RNH2, right? Basically, HI will be removed. But this reaction keeps on going. You can form RNHR, you can form RR, and triple bond this thing, and eventually you can reach with R4N plus I minus. Quaternary ammonium salt also you can form, right? This reaction looks okay because eventually you are forming this RNH2, right? But we'll see whether any other thing is given or not. Okay, right. Next, I'm going for alcoholic AgNO2. And alcoholic AgNO2 doesn't do anything. At least if it is aqueous AgNO2, you would have removed this and put NO2, right? Alcoholic doesn't do anything. Okay. Next, NaN3 and sodium and this. NaN3, you don't know this reaction. Okay. If you have, say, Ri, right? And you go for NaN3. Now the nucleophile here is N3 1 minus. This ion is what is called as your azide ion. Okay, this N3 1 minus, right? Ion is there. That's what is called as azide ion. Okay. Oh, but it's NaN3, right? Okay, NaN3 sodium ethoxide is there, right? So what are we trying to do here is that this ETOH and Na can react to form ETONA. That is basically nothing but CH3, CH2, O minus, Na plus. Is it not? Right? Now what ion is coming here? NaN3 ion is coming here. So this entire thing now will be replaced with N3. That's what will happen eventually. Right? So again, why you're not forming the required product. So obviously the most probable answer, even though it's not a good method, but still we'll be going for this. Okay, that is producing your RNH2. That is converting the iodine into NH2. Okay, next. Which of the following is urotropine? What is this? Anything given regarding this in your textbook? Urotropine? I don't think these are not part of syllabus. Urotropin is a white crystalline organic compound with formula CH2 6 times N4. Oh, okay. It should be then 4 methyl groups, 4 NH2 must be there. That's what I understand. Right. So if I go there, hexamethylene triamine, none of this, hexamethylene tetramine. Yeah, 4. So urotropin is going to contain 4 NH2 groups. That's what I understand. Okay, 4 nitrogen should be there. Only tetramine will have 4 NH2s. But anyways, I think this question is completely out of syllabus. Moving on. Okay, so benzylamine. What is benzylamine? That is this C6H5CH2NH2. That is benzene ring with 1 CH2 and NH2. Right, and one NH2 like this. Okay, is reacting with RX. Obviously, you can expect nucleophilic reaction to happen. So if I have RX, say you have X and R, and you will remove 1 HCl to form this particular compound, C6H5, CH2, and HR. Right. Which of the following alkyl halide is the best suited for this reaction through SN1 mechanism? Now that's very simple, right? In SN1 mechanism, this particular RX, which undergoes the nucleophilic substitution, should be tertiary. Is it not? The order of reactivity is what? This one is the order of reactivity, right? Tertiary greater than secondary greater than primary for alkyl halides and aryl halides in SN1 mechanisms, right? Or somehow if I can get a stable carbocation, or it's all about a stable carbocation which is getting formed. C6H5Br. First of all, this will never ever undergo nucleophilic substitution because the Br is direct as the benzene ring. C2H5Br is primary. CH3Br is primary. What about this one? This one is also primary, C6H5CH2Br. But if you understand this carefully, if I go for this CH2 plus, which is going to get formed after the Br minus leaves, is very highly stable. Why is it stable, people? It is even more stable than tertiary. Why? Do you know? Why? Because it's very simple, right? You see that these triple bonds are there in the benzene ring, will involve in resonance with this. It is resonance stabilized. That's the reason why this carbon is going to be very, very highly stable. This is a very general rule, Kana. Right? Tertiary more stable than secondary, greater than primary. It's a very, very general concept. There are so many things you have to understand if you want to go for JEE mains level or even NEET exams level. Right? Anyways, this is stabilized by resonance. So that is the one that is going to form your most stable carbocation, and that is the best suited alkyl halide because that is what is going to react the most efficiently. So answer is C. Okay, moving on. Central nitrogen of the diazonium group has dash many number of bonds. What kind of bonds we have? Okay. So if I can just write it, it is N2 plus Cl minus, right? So I mean Rn2 plus and Cl minus. Or if I just take any one example also, CH3 N triple bond plus. This is what is N2 plus. Okay. Now, if you are wondering how am I getting this, we can draw the Lewis structure if you want to check, right? Say for the central nitrogen, I'm going to have 5 valence electrons, right? And for the other nitrogen atom also 5 valence electrons, right? 5 valence electrons. Okay. Now this nitrogen is having a positive charge. So instead of having 5 valence electrons in the central nitrogen, we'll have only 4 because there is a positive charge, right? And I'm going to have a carbon. Obviously, other 3 hydrogens will satisfy them. I'm talking about only one bond, which is here, right? Fine. Now you understand that this nitrogen requires 2 electrons. This nitrogen, 3 electrons. This nitrogen requires 3 more electrons to satisfy its octet. So it will take up these 3 electrons. This nitrogen will take up these 3 electrons, right? And obviously 3 more hydrogens are there. That will be again 2 electron pairs shared. Again, carbon requires one more, right? One more. What is that? This thing to complete its octet. Done. Right now, what are you seeing? We have a normal triple bond between the 2 nitrogen atom, and this nitrogen is having a positive charge and having a normal single bond with your carbon atom. Right now, how many sigma? Okay, we'll try to understand this. So they're telling 3 covalent, 1 coordinate. Where is coordinate bond now? Nothing. All we have is this nitrogen has 4 what? 1, 2, 3, 4. 4 covalent bonds. It is nothing else. There's no coordinate bond. Nothing here. What is coordinate bond? Nice. What is the coordinate bond? You're going to write your board exams and you don't know what is the coordinate bond? You have read coordination chemistry, right? Coordination, what is that? Coordination compound chapter you have? Do you have this at this time? This or last semester you had? Do you have coordination compounds this time or previous time you had? I don't understand what this silence means. Guys, are you there?
Yes, sir.
Okay, I'm asking coordination compounds. One chapter is there. That was this time or previous time? Okay, if you're wondering about what the chapter is, the bracket, something FEC and 6, everything.
Yes, sir. We have it.
Oh, you don't even, oh my God, you don't even remember the chapter names. Even
No,
though,
sir.
right?
We know.
Ah. Oh, okay, fine. So this coordination chemistry is nothing but coordinate bonds, right? What kind of bonding exists between your ion and CN here? you have IN3 plus, for example, and you have CN minus, you have a lone pair on carbon. This lone pair gets donated and the bond is a single bond, right? But here you see what is happening. Fe is not bringing up any electron, right? Both the electrons are going to come from, what is that, Cn minus, is it not? Right? And this kind of bonds are what are called as coordinate bonds. It's not mutual sharing. One species will donate 2 electrons, and other will just take up electrons, and both the electrons will be mutually shared. Right? Okay. Fine. Anyway, so answer for this question is only 4 covalent bonds. Okay, next. Which is the most volatile? Okay. Now, when they're asking about volatile, they're asking about least boiling point, is what they're asking. Obviously, whichever is going to have the least boiling point, they'll be more volatile. They easily evaporate. That's what you mean by volatile. Okay, right. So now we have the secondary amine, we have a primary amine, we have a tertiary amine, and we have an alcohol. Right? Now, how do you choose this? I think you know this. So the boiling point, how will you have 3 criteria to look at. One is the molar mass, more and more molar mass, more and more is the boiling point. Second one is the branching. And third and most important one is hydrogen bonding. If you have hydrogen bonding, these 2 doesn't even matter. This is what is going to be deciding factor. Okay. Right. Now, can I say that in this molecule, you have a hydrogen donor, that is NH bond is there, and a lone pair is also there in nitrogen. So this can definitely involve in hydrogen bonding. Right. Same goes with this one. You have a lone pair and you have NH bonds. This can also involve in hydrogen bonding. Same goes with this one, because oxygen has a lone pair and OH bond is there. This can also involve in hydrogen bonding. Right. But if you check this one, this has a lone pair, but nitrogen does not contain any hydrogen. Right. So this cannot involve in hydrogen bonds, whereas all of them can have. So this is the one which is going to have your least boiling point, and that is going to be the most volatile one. C will be the answer. Okay. Right. Moving on. Okay. Which gives primary amine upon reduction. Okay. Now this is an isocyanide. Isocyanide on reduction would give me what? This compound would have given me CH3CH2 NHCH3. This is what would have happened for this compound. You already just added hydrogen to this. This is a secondary amine, right? Now, upon reduction, this, if I go for reduction, I think all you have to add is add a hydrogen to this. So nothing would happen. Okay. And this one, right? You have ONO. Now, if you try to reduce this, you will get maybe this one. ONH2 you'll
Sir.
get. This is not, yeah.
Sir, in last question,
Last question.
more volatile will have least boiling point, you know. You told us.
Yes, most volatile will have least boiling point. Yes.
But boiling point is proportional to hydrogen bonding.
Okay.
So, okay.
So other 3 has boiling point. Other 3 has hydrogen bonding, so they'll have high boiling point. So this C doesn't have boiling point. This C doesn't have hydrogen bonding. So obviously that is going to have the least boiling point. That means it is going to be easily volatile, most volatile.
Okay,
Right?
sir. Thank you, sir.
Okay. Right. Fine. So again, this kind of compounds cannot be this thing. But now you see that this one is going to be CH3CH2N double bond O with the coordinate bond. Now you see in a nitro group, there's going to be a coordinate bond from nitrogen to oxygen. Anyways, so now if you reduce this, if you go for reduction of this, what will you give? If you see nitrogen is directly attached to the carbon now. Now that will definitely give me NH2 like this. Okay, right. So definitely D will be the answer to this question. Right. Okay. Moving on. Method by which aniline cannot be prepared. Okay, aniline you should not be prepared. You'll be prepared. Potassium salt of phthalimide treated with chlorobenzene followed by hydrolysis with aqueous solution. What reaction is this first? This is your Gabriel phthalimide synthesis. Right? Now, what I'm trying to understand is you have to remember the reaction. I think I only thought your amines, right? Do you remember the mechanism for this? Guys, do you remember the mechanism for this?
No, sir.
See, this is what happens. So we have phthalimide. Phthalimide is C double bond O NH. Again, one more C double bond O will be there, right? Now, what first short you have to use is your KOH, right? Now, this KOH is going to take up this acidic hydrogen. This hydrogen is acidic enough, okay? So, you will form C double bond O N, C double bond O N, and this is going to be N minus and K plus, okay? Now, if you go for any alkyl halide RX, now using there's going to be a negative charge on this nitrogen. This comes and attacks here, and this X minus leaves. So now what will you have? We will have the benzene ring. We will have C double bond O. We will have one more C double bond O. But instead of the K, we would have had N with R because it had attacked the alkyl group. Now what will you do? Now you will go for hydrolysis. H3O plus you will add. Now what will happen? You see that this bond is there. This bond is there. You will break it, add hydrogen, OH. Break this bond, hydrogen and OH. Now what will happen? RNHH. So that is going to form your RNH2. And obviously the side part is going to be C double bond O, C double bond O, and that carbon is now having OH, and that carbon is again having OH. That's what is coming, OH and OH. This is what is called as your phthalic acid. Okay. Anyways, so you are able to form a primary amine from this.
Sir,
Yes.
sir, but phthalimide is benzene ring connected to CO and that CO connected to another benzene ring, no, sir.
No. This is what is phthalimide. Okay, this is what is phthalimide, and this is what is the reaction is. Okay. Now, how do I understand whether in this case, this R, which we write here, again, it is going to create some problem, but please bear with it. This R, which I'm writing, I hope you're seeing it. Right? Now, this R, if it was benzene ring, will this reaction happen? Or why it won't happen? That is, if you had, for example, what they are telling that is your chlorobenzene, that is C6H5Cl, right? Now, no benzene substitution can happen in case of nucleophilic reactions, right? Where is reasons again? Excuse me. Partial double bond character, something you have studied. Okay, so chlorobenzene does not undergo any nucleophilic substitution. And that's the reason why this R here cannot be NH2 again. That is meaning this R cannot be C6H5 again. Right? So obviously that Gabriel phthalimide synthesis, you will not be able to produce any secondary amine. That is not possible. And one primary amine we cannot prepare, that is your aniline. C6H5 NH2 will not be able to prepare. I even told this point while I was teaching Gabriel phthalimide synthesis. Right? So option A is the answer to this question. Right? And degradation of benzamide with bromine and all, you can just go through this thing and you'll easily understand what is going to happen. Okay. Right. Moving on. Right. Nitrogen's lone pair in pyrrolidine is the best. Okay. Why is it not again not happening? Okay, just a second, guys. It's gonna happen again like that, I guess. Okay. We'll just try it again. Okay. Pyridine, again, I don't think you are required to know this. Anyway, I'll show you how pyridine looks. Okay, this is what is pyridine, right? What is that? A 5-member ring with nitrogen. Okay, so if I can just draw that there. Okay, this is what is this, right? Now you see there will be one more hydrogen atom also, and there will be a lone pair on this, right? Now you see that how will you calculate the hybridization? You look at the steric number. Steric number is equal to number of bonding atoms plus number of lone pairs on the central atom, right? Now you see 2 nitrogen, how many are bonded? 1 hydrogen, 1 carbon, another carbon. So this value is 3 plus number of lone pairs. Now this lone pair is there, plus 1 will become 4. Now moment you see it's 4, you can conclude that it is going to be sp3 hybridized. Do you know this, how to calculate the steric number and how to calculate the hybridizations? Do you know or you don't know? Again,
Yeah.
what do you mean is, tell it, what is it?
Yes, sir.
Oh, okay. See, this formula will remember. Okay, I'll show you one formula, and with that formula, you can easily find it. Let me show you. Right. Right. Say now steric number formula is this: number of atoms bonded to the central atom, Ca is central atom, plus number of lone pairs in your central atom, right? So now steric number value 1, 2, 3, 4, 5, 6, 7 is possible. Now 1 is not possible, sorry, minimum is 2, right? So 2 is sp, this is sp2, this is sp3, this is sp3d, and 6 is sp3d2, and 7 is sp3d3. That's it. All you have to remember is the formula, and with the steric number, what hybridization. That's it. Okay. Right. So sp, sp2, sp3, sp3d, so on and so forth till 7 sp3d3. Okay. Now you can easily find any types of hybridization here.
I have a doubt, sir.
Yes, tell me.
In the formula, what is that second one, sir? The number of
A number of lone pairs. Like you calculated in this example, right? What you did for nitrogen. You calculate how many atoms are there? 1, 2, and 3. Right? And there's one more lone pair also on the nitrogen. That also you took. So it becomes 3 plus 1 number of lone pairs becomes sp3.
okay, sir.
Understood?
Yes.
Okay. Right. Moving on. Next this question. Okay, I'll just put it here. Right. Let me little zoom it. Okay. Write the chemical equation for the following reaction. A primary amine is prepared from a primary alkyl halide. Very simple. I have an Rx that is okay. We can write an example also. CH3Cl reacting with a primary amine is prepared. NH3 to form what? CH3 NH2. That's it. Right. This is an example. A primary alkyl halide is this CH3Cl, right? Reacting with NH3 to form CH3 NH2. That's what they're asking. Very simple. Next. Write one reaction for each illustrate your acetylation. Okay, for acetylation, say you can write, for example, if I have CH3 C double bond O Cl, right? Now that I'm going to make it react with CH3 NH2. For example, what will you do? You'll remove one hydrogen and one chlorine and go for CH3 C double bond O CH3. Right? So whenever you add this particular group to anything, right, any kind of molecule, that because this is what is called as your acetyl group, right? And if you add this acetyl group to any compound for that matter, the reaction is going to become acetylation, right? So remember that acetyl group is CH3C double bond O group. As when you add the acetyl group to any carbon, any compound like this, in case of CH3NH2, the entire reaction becomes acetylation.
Sir, what you have removed from this?
Basically, if you have to show you CH3, C double bond O Cl, H, N, H, CH3. We are going to remove HCl. Okay, now this C double bond O will directly attach to this nitrogen, and that's how you get this compound. Where is it?
Sir, in the
Oh,
product, there is no nitrogen.
I'm so sorry. This will become NHCH3. Yeah, I just forgot this NH. So that's the final product. Okay. Right. Next, you have Gabriel's alignment. This just now we saw. How will you write a general reaction? So you will take this thalamide, C double bond O, C double bond O, NH, all what only you can put, KOH you have to put, RX you have to put, and you have to go for hydrolysis. And eventually you'll end up with RNH2. You put R as anything and then go for this reaction. Say CH3 or C2H5, whatever you want you put and complete this reaction. Okay, right. Next. Arrange the following in the decreasing order of the pKb values. Now, please understand, people. When they ask you about Kb, right, that Kb is directly proportional to the basic strength. Right? But if they ask you about pKb, that is inversely proportional to the basic strength. Right? That number. Okay? So, strong bases will have very less pKb values, whereas strong bases will have very large Kb values. Okay, right. Now, how do you decide the basic strength? It is just that it is going to be directly proportional to the availability of lone pair on the nitrogen.
Or more electronegative atom.
No, we are talking only about nitrogen is this thing here, so we can try this thing. A more available lone pair on the nitrogen atom, right? So all of them are going to have a lone pair, lone pair, lone pair, lone pair, right? Now you see that C2H5, that is an R, electron donating group. So there will be a chance that this will increase. The amount of lone pair will increase, right? Now you have a CH3 group this time, and that is going to increase it. But this C6H5 is benzene, right? So whenever you have benzene ring directly attached with nitrogen, say NH2 is there, right? This lone pair is not available on this because it is involving in resonance, right? So that particular lone pair is not available. Whenever you have resonance happening, the basic strength is decreased because the lone pair is not available, right? But here I have at least one electron donating group this time, so it's okay, right? Now this time I have two electron donating groups, C2H5 twice it is. So twice increase will happen. And in this case, you have just aniline ring, so it is going to involve in resonance. But here slight increase might happen because of CH3, right? So where am I having double increase? Definitely this one, C2H5 twice NH is having the maximum availability of lone pair. Then comes this one, that is C2H5NH2, right? Then comes the one which at least has one CH3, that is C6H5NHCH3, and the least of all, that would be C6H5NH2. That's it.
Sir,
Okay. Yeah.
sir, what you wrote first is more basic, right?
Oh, we're talking about, okay, this is the basic strength order. Okay, whatever here you wrote is your basic strength order. Reverse would be the order of the pKb values. Absolutely. Right. That is because we see pKb and basic strength are inversely proportional. Right. This, whatever we wrote, is the order of basic strength. Once you complete that, reverse the order to get your pKb order. Understood? Right. Okay, if you have any doubts, you have to ask me. This is the time. Please don't keep mum. Okay, fine. Moving on.
Sir,
Okay.
can you show?
Yeah. Tell me.
Can you show the? Yeah, 1 minute.
Ah, sure.
Sir, among C6H5NHCH3 and C6H5 and NH2, which is more basic, sir?
Obviously this one. But I wrote something, right? That didn't happen. Oh, the last one. Okay. After this ordering should come. Okay, let me write the order in some other slide. Wait. What is wrong? Okay, this one, right? Right. So I will just add a blank page. Okay. Right. So the order goes like this. The basic strength order is C2H5 ties twice NH. Then your C2H5NH2. Then comes your C6H5NHCH3. And the last is C6H5NH2. This is your basic strength order. Right? Reverse will be for PKB.
Yes, sir.
Okay. Right. Okay. This question. Okay, just maybe let me make it a little. Okay, right. So example you have to give for ambident nucleophile. Ambident nucleophile means it will be able to attack through two different atoms. I think I write this in your alkyl halide chapter, I guess. Say for example, if I have Cn minus and Nc minus, right? Now if I go for RCl with your KCN, you remember that I'm going to get Cn, but if I go for AgCN, I'm going to get RNC. This is your cyanide, this is your isocyanide, right? These kind of things are what are called as your ambident nucleophiles. Or you can even have NO2 minus, ONO minus. That is also okay, right? Fine. Next, Hinsberg test. Now you know what happens in Hinsberg test, right? I have to make a new slide for this, right? Right. So what happens in Hinsberg test? So you will take primary amine, make it react with C6H5, C double bond O, SO2Cl, right? Cl, S double bond O, and C6H5. That is benzene ring. Now what will you do? You will remove one HCl, right? You will remove one HCl and you will form RNH, or I'll write like this: RNH S double bond O, C6H5. Right now, if I try to put KOH here, you will get a completely dissolved solution because this hydrogen is acidic. Right, but if I go for your secondary amines, just a moment, RNH R, and you go for Cl S double bond O, C6H5, you will be able to remove these two. No issues. That is HCl. You will form RNR SO2, that is S double bond O with C6H5. Right? Now, if you try to put KOH, right? Now you see that this does not contain any hydrogen. So this will be not dissolved. Right? Whereas if we take tertiary amines, if I'll just write it here, tertiary amines, what is going to happen? If you take RNRR like this, and you go for Cl S double bond O, C6H5, no reaction would happen. Why? Because there is no hydrogen atom here, first of all. right? This is how you use this Hinsberg test for what? You use it for separating or say distinguishing between your primary, secondary, and tertiary amines, right? Tertiary amines will not even react. You're seeing it, no reaction is happening. Whereas if you go for primary amines, they will react, and that particular compound will be soluble in KOH because it's still acidic hydrogen there. Secondary amines will react with this, it will form a product, but that if it dissolve in KOH, it will not dissolve because this other amine has acidic hydrogen. Right? This is what is called as your Hinsberg test or Hinsberg reagent. Hinsberg reagent is this one. This, whatever you're adding here, is what is called as your Hinsberg reagent. Hinsberg reagent. This is CLS, so I mean CLS double bond to C6H5. Right? Okay. Moving on. Right. Write the final alkylation product of aniline with excess of methyl iodide in the presence of sodium carbonate ion. Now they're asking, we have aniline, right? That is going to react with excess of methyl iodide. This is CH3I, excess. And we know if it is going to be there, reaction is continuously going to happen. Whatever hydrogen atoms you have, everything you will replace with your CH3. N, CH3, CH3. Right? This would be the final product. Is it not? Okay, basically you'll go for HI from this. Again, one more time HI from this. So both sides methyl group will come. That's very simple to understand. Minus 2 HCl. 2 HCl. Sorry, 2I it is. Okay. Right. Moving on. Okay. An organic compound A contains molecular formula C3H7O2 on reaction with Fe and concentrated HCl gives compound B. Okay, right. With the molecular formula of C3H9N. Now you understand, right? C3H7O2N. And now this is a reducing agent, right? Metal bar HCl, tin bar HCl, Fe bar HCl is a reducing agent. And you see 2 oxygen atom, 1 nitrogen atom, and C3H7. So all I can think about is 3 carbon atom having NO2. And that on reduction is actually giving me CCC with NH2. That is what is happening. NO2 will get reduced to NH2. Right? That will be CH3, CH2, CH2, NH2. This would have been the product. Right? Okay. Compound B on treatment with NaNO2 plus HCl gives another compound C. That is, if I go for NaNO2 plus HCl, that is your diacidization reaction. This is going to form CH3, CH2, CH2, N2 plus Cl minus. But please understand that aliphatic diazonium salts are very, 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 very unstable. Okay, aliphatic diazonium salts are very, very unstable. So they will not be like this. Okay, they will react with water molecule which is there to convert. This will attack here and this N2 completely leaves. So you will eventually form CH3, CH2, CH2, OH. This is what is going to be there if I directly put NaNO plus HCl in that with an aliphatic amine. Right? Because aliphatic diazonium salts are very unstable. Okay? Right. Now this particular OH group is going to be there. That is your compound C. This is your compound A. This is your compound B. Right? Okay. Now C gives effervescence with OH, Na. Obviously, why? Why? It will obviously, if I make it react with sodium, what do you understand this? This is an acid. So you will form C with O minus Na plus, and obviously that is going to give me some hydrogen also. And this hydrogen is the reason where I'm going to have effervescence. Okay, right. On oxidation with CrO3, compound C gives a saturated aldehyde. And obviously, right, if I make it undergo oxidation, that is, if I add CrO3 to this, this is going to become CH3, CH2, sorry, not CH2. I will write this in the next page. Right, so if I have CH3, now what is the problem? Oh, wait, I have to connect my charger. Just give me a second. Okay. Yeah, I was trying to write something here. So basically, the C compound which we formed was CH3, CH2, CH2OH, and obviously on oxidation, that is CrO3, is going to give us CH3, CH2, and this entire CH2OH is going to become now CHO. That's it. Right? This is your compound D. That's it. Very simple. Right? They're asking about A, B, C. Okay, D they're not asking. If at all they asked about D, that is also there. A, B, C, we can write. Right? 3 carbon atom with NO2, 3 carbon atom with NH2, 3 carbon atom with OH. These are the things with ABC. Right. Moving on. Next, how would you achieve the following conversions? Write this thing to write the chemical reactions. Nitrobenzene to aniline. Very simple, right? Again, you have what? NO2.
HCl.
Right? I have to convert it to NH2. All I have to do is go for reduction. Say I can go for SN bar HCl. That's okay. Or you can go for H2 bar nickel. That's also okay. Right? Next, an alkyl halide to a quaternary ammonium salt. We have seen this 1,000 times. Rx plus NH3. First we'll give primary amine, then secondary amine, tertiary amine, and then eventually quaternary ammonium salt. Okay. Right. Next. What is this? Aniline to benzonitrile. What is benzonitrile? Aniline is this. Right? Benzonitrile is this. NC. As isocyanide. What do you have to put here? Can't you understand? This is going to be a carbylamine reaction. A primary amine gives isocyanide. This is a foul-smelling compound, right? Right? So carbylamine, what do you have to put here in this case? Right? You actually have to put CHCl3 plus KOH. This is what you need to put. Right? So if you can just write the general reaction for carbylamine reaction, if you have RNH2, if you go for CHCl3, if you go for CHCl3 in the presence of KOH, you are going to form RNC. Okay? That is a foul smelling compound. If you get the foul smell, then we can understand that is a primary amine. Secondary and tertiary amines will not react. They will not give any reaction with this CHCl3 and KOH. Okay? Right. Moving on. What happens when nitropropane, or again, nitropropane is
Sir,
CCC?
can I zoom?
Can I zoom? Sure. Okay. Right. Nitropropane is treated with LiAlH4. That is, if this treated with LiAlH4. Okay. LiAlH4, I know what reagent is, right? Reducing agent again. Is it not very strong reducing agent? Right? Obviously, it's going to reduce your NO2 to NH2. That's what is going to happen. Next, ethyl isocyanide undergoes hydrolysis. That is CH3, CH2, NC on hydrolysis, H3O plus. Now, all you have to understand is break this bond and add H here and add some amount of OH here. So you will form CH3, CH2, NH2, and one carbon atom with the carboxylic acid will become HCOOH. Now, how do I explain this to you? Let me make a page. Let me write it here. Right? Say if you have this R, N, C, and you go for H2O, what will you do is you will break this, right? And put hydrogen here and OH here, and you'll put 3 OH groups here. Right? So if you put carbon atom with 3 OH groups like this, what will happen? You will remove one water molecule like this to form C double bond O with one OH. That's it. Okay? Fine. Anyway, so you're going to form acid part. That's what is going to happen here. So that's the same thing happened in the previous reaction also. Right? You're going to form CH2, CH2, NH2, and you're going to form one carbon carboxyl, this methanoic acid. Right? Okay, next. Predict the reagent of the following. So we have CH3NO2 to NH2. Again, how many times? SN bar HCl would be the answer. Okay. Now this, converting into this by adding this, that's okay, right? Then we are going for HNO3 and H2SO4. Now I understand that This is going to be okay activating. This is going to be more activating than this, because if I compare NH2's activating power with CH3's activating power, definitely this is going to be more activating, right? But if I compare NHCO CH3 with your CH3, definitely CH3 is going to be a better activating group. Okay, right. So based on that, you will decide. So definitely this is an ortho-para-directing group, and this is nitration. So you will get your this thing to be CH3 here, and N double bond O and C double bond O CH3 here, and obviously the para position already occupied. No, nothing you can do. So, but in the ortho position, you're going to get NO2, right? And this compound on reaction with something is forming what? Is forming your NH2 back. This particular thing is getting back to NH2. That is nothing but hydrolysis, H3O plus.
Sir, but we are having NO2 in meta position.
Oh,
The nitration.
yeah, nitration only. That's okay. But I think they're asking about other possibility. This particular thing, whatever I wrote here, would have been the major product. But they are assuming that they're not taking the major product, they're taking the minor product. That would have been the ortho position of this getting occupied. Right. Anyways, you can understand this from this data. That is NH2. Anyways, right? And then you're going for Na2 bar HCl. Obviously, Na2 bar HCl will be converting this into N2 plus and Cl minus. Is it not? Wherever I have NH2, that would have become N2 plus and Cl minus. And something you're adding, and so that this entire thing is removed now. What you have to add here? Obviously, if you have N2 plus Cl minus, now if you want to convert it into benzene, what you have to add here? You have to add H3PO4. Okay, you have to add H3PO4 so that diazonium salt gets converted into your benzene. Okay, right. So these are all the answers of these questions. Easy things. Okay, moving on. Right. For the following conversions, write the chemical equations. Okay, ethyl isocyanide to ethylamine, that is CH3, CH2, NC to get converted into CH3, CH2, NH2. Now, all I have to do is break this bond. All I can go for is H3O plus. Direct hydrolysis will give me. Right? Next. Aniline to, okay. Right? Aniline to N-phenyl ethanamide. Okay. Aniline is this. And I want to convert it into N-ethyl, N-phenyl. This is what is N-phenyl with your ethanamide. Ethanamide is C double bond O with CH3. That is, this is what is ethanamide. Nitrogen, carbon, that is carbon, C double bond O with nitrogen, what is amide. And here it is going to be ethanamide because 2 carbon atom. And to this nitrogen, phenyl group is attached. So it is N-phenyl. Right? Okay. Now, definitely this is going to have one hydrogen also, no doubt about it. Right? Now, how do you grow this? This is what is your Scott and Bowman reaction, right? Right? What do you do with Scott and Bowman reaction? You will go for NH like this, and you will make it react with, you will make it react with Cl, C double bond O, CH3, right? And what will you do? You will attach this nitrogen with this carbon. Acetylation, basically. Right? That's what you will do. Right? Fine. So that's what you have to do now. Okay. Next, B option, this thing. Okay. 2 isomeric compounds A and B having molecular formula C4H11 and both lose N2 into the HNO2. That means both are primary amines, right? If you have RNH2 and that reacts with NaNO2 bar HCl. Right now, obviously, I told you that they will not form the alcohols. I mean, they'll not form the diazonium salts because they're very unstable. Eventually, they will form this thing with N2 gas getting liberated. And this will happen only if I have primary amines. Okay. So both the isomers are having primary amines in them. Okay. That's what I understand first. Right. Gives compound. So, okay. A is reacting with HNO2 to give C, and B is reacting with that to form D respectively. Okay. C is resistant to oxidation, but immediately responds to the Lucas test. So now C is resistant to oxidation. That means, okay. We know what is the capacity of undergoing oxidation also, right? That is, primary ROH can be easily oxidized. Secondary is okay. Tertiary, not okay. Primary, if I oxidize, you're going to get RCHOs. Secondary, if I oxidize, you'll get RCO, double bond Rs, and tertiary, nothing will happen. Right? Okay. So they're talking about actually secondary here. Right? Secondary is resistant to talking about resistant to oxidation. That means it is tertiary. That is, it is not going to undergo any oxidation. Right? Whereas primary is the undergoing oxidation. Right? So what I understand is, so this 4 carbon atoms which I'm going to have, one of them is going to have NH2 like this, like directly primary attached, right? Whereas the other one should be having only 3 carbon atom on 1 carbon as a branch, and this would have been an NH2. Now this NH2 would have become OH. Now what happens? You form a tertiary alcohol now, right? If this NH2 becomes OH, you form a primary alcohol, right? But this NH2 becomes OH, it is going to become tertiary. The tertiary will not undergo oxidation, but Lucas test, obviously, it is going to, react the fastest. It is going to give the turbidity at the least time, right? So A and B should have been what? A and B should have been like this: CH3, CH2, CH2, C4 or C, how much? C4, right? Okay. CH2, NH2. This would have been your A, and you would have had this one to be your B. That's it. And eventually you convert them into your OH, that becomes your C and D. Right? Okay. Moving on. And I think we are done. There are no more questions. Okay. Any particular doubts anybody has?
No, sir.
Okay. Fine then. We'll see you next week. Right. Thank you so much.
Thank you, sir.
Thank you, sir.